Hey, good afternoon, everyone. Welcome to this talk on Akka and Kubernetes, the beginning of a beautiful relationship. My name is Hugh McKee. I work for a company called Lightbend, and I've been there just about 3 years, just coming up on 3 years. My role is a developer advocate. But before I came to Lightbend, I worked for a long, I'm not going to tell you how long, because I'm too old, but a long time at Hewlett Packard. And a good part of my career there was in consulting, and then around the 2000s I got into internal IT. And at the time, HP was around 350,000 employees. So we had a pretty big, typical enterprise environment. And if you look at my bio says I've got this long career. I don't remember exactly what it is, but it's something. I've got this long career of building brittle systems that fail often. Because when I was in IT, not only did I have to build systems, and I was, a developer, I was an architect, but also did production support. And I learned of my mistakes. The things I do when I design a system or I build a system, it goes into production. If I did something bad, I paid for it because the system would go down, the system would break. And we were on 24/7 systems. They were customer-facing, and when they went down at HP, they called them escalations. There was this formal thing where everybody got together, and didn't matter what time of the day it was, a weekend, at night, whatever, and we'd be on the phone trying to fix this problem until it was fixed. So time after time after time, I was in these production support issues going, how do I program my way out of these things? What can I do to not have to deal with these kinds of production outages? Well, after about a decade of that, learning and suffering and swearing at people that didn't know how to write good log, messages and log files, getting log messages that were ambiguous, or just trying to diagnose what in the world was wrong with the system, I took an online course in Coursera on Scala back around 2013. I was kind of on this kick of taking classes. And at the end of the second class, I came across, they had a section on Akka, which is the actor system running on the JVM. So if you look up the actor model, for example, you'll see on Wikipedia that it was originally proposed in the 1970s. Well, about 10 years ago, and actually it's the 10-year anniversary for Akka, one of the co-founders at our company started an implementation of the actor model on the JVM with Java or Scala APIs. And a few years later, they added a feature where the actor model wasn't constrained to a single JVM, but could work in a cluster. And it was shortly after that I came across Akka. I had never heard of Akka before. I'm a Java developer. I've been working with Java since when it came out in the 90s. And I saw this thing in this class, and it's like, wow, this thing looks really interesting. It's like, not only can I write code that runs in a single JVM, but I can run multiple JVMs that kind of work as a single JVM. So I went back to my team, and at the time we had this project that was really driving us crazy with reliability. And we were building this system with the typical, at the time, high reliability, like an active-passive failover type of situation where we had 50% of our hardware just sitting there waiting in case the primary failed, we'd fail over to the secondary. And one of the most annoying things about this was half the time the failovers didn't work. And we were just really desperate. So when we came across Akka, I came back to the team and I said, hey, this thing looks really interesting. Why don't we take a look? Long story short, we took a look at it. We decided to go forward. We rewrote a system that we'd already written, Java, Tomcat, whatever, active passive failover. We rewrote it in Akka so that it could run in a cluster, and it was marvelous. I mean, for me, it was amazing that we could build a system that was hard to break. We could do like rolling updates. We could kill nodes while the system's running, and the system would keep working. And to add to that, the fun was kind of wrapping my head around what's it like to program in actors. So programming in actors is different. Some people say it's hard, and I say it's not hard, it's just different. When you learn something new, it initially seems, why are they doing this way? But then eventually you get into it, and it's like, oh, this makes sense. And then as we were building this system, or writing this system and architecting it, we were going, well, we kept asking ourselves, well, okay, we lost a node. What are we going to do? And we look at the actors that were involved and go, well, we could do this and we could do that. And it was like, oh, man, we can solve this problem. So I just fell in love with it. I mean, I was like, this was the best thing I'd ever seen. And I've been writing software for a long time. So that got me into Akka big time at HP, and then kind of led into getting a position at Lightbend. So Lightbend, if you're not familiar with the company, in addition to Akka, which is an open source Java or Scala actor model into JVM, we're also the company that's behind the open source Scala language, object functional language. And there's a Play framework, which is asynchronous web framework, and then Logon, which is relatively new, is a microservice framework. But I'm here to talk about those things. I'm here to talk about the love that Akka has for Kubernetes. Because, as I mentioned, Akka, for a while, could run in a cluster. So the nice thing was, inside the JVMs, we could build systems that could handle, like, running on n number of nodes, like running on 3 nodes or 50 nodes or things like that. Some customers have gone up to hundreds of nodes in Akka clusters. In my experience, it was more on a smaller scale, but the thing was we could run on multiple nodes. But the part that we were missing was something to manage those nodes, because Akka can react. If you start up another node and it joins a cluster, Akka can say, oh, we have more capacity. We can move actors over there. We can start using that. And I'll show you that in a little bit. But the part that was missing was kind of the management of these nodes. So along a few years ago comes Kubernetes, where we have kind of this perfect marriage. Kubernetes is this beautiful platform for managing. The way I look at it is, I'm a Java developer. The way I look at it is places to run my JVMs. And I don't have to think too hard about it. I basically just say, here's a JVM running in a Docker container. Thank you very much. Run it. And if it needs to scale up, it can scale up. If something fails, Kubernetes takes care of it. So in a way, Kubernetes is handling things on the outside of the JVMs, running the JVMs, while Akka is running things on the inside, handling the actors. And that's what I want to show you here. So what I've got is a setup on my laptop using Minishift. Minishift is the OpenShift version running on a laptop. You can use Kubernetes straight itself, but we've been doing a lot of work with Minishift, so I've been using that. So you can run commands. There's Minishift commands. There's OpenShift commands, like show me what pods are running. And if you're not familiar with Kubernetes, I'll explain what those are in a minute. But you can also run Kubernetes commands. They're called kube-control. And just things like that. But also running on the laptop, though, is a nice, kind of the user interface you get when you run OpenShift for real, in a real cloud. But here it is, it's just running on my laptop. So what I've got running here is a single container running a JVM, and I can see what's running in this environment, but I also got a load balancer set up that this is all running on my laptop, just a software load balancer. And I got a little front end that I wanted to show you that kind of visualizes what's happening in the live system. So right now, this system's running. It's a simple project. It's a Java Maven project, and I'll give you the GitHub repo at the end of the talk, with this visualization on top of it. And the visualization's just, anybody hear of D3.js? It's a JavaScript framework that's really cool for doing visualizations, because I'm not a JavaScript developer, but I was able to make this work, basically. Really cool, though, because you get these nice-looking visualizations. So what's happening is that the cluster's running, and I'm kind of simulating things happening. So you can, as we go through this, kind of think about this as like a single microservice, okay? And I'll explain what everything is, all these little circles are in a moment. But somebody in my company called it a crop circle. You guys know what a crop circle is? Yeah, supposedly when UFOs land and they decide, they come to Earth and they decide they're going to go into a field of wheat and flatten out a bunch of circles, but not contact us. But anyways, somebody called it a crop circle. But really what this is showing is, this visualization is showing the cluster running. So here what I'm trying to show is that there's 3 JVMs running in this situation. And there's kind of a tree that comes out of each JVM. So if I go back to this console and I can scale it up, I'm going to go from 1 pod, which is 1 JVM, and we'll scale it up to, let's scale up to 3. So I'm telling Kubernetes, hey, would you run some more pods for me, which runs some more Docker containers, which runs some more JVMs. So we're going to scale up to 3 JVMs. So Kubernetes is spinning this up. The JVMs are starting up. Now my little UI thing here, in a few moments, what we'll see is these pods will show up, and then we'll see things start to migrate to these new pods, to these new JVMs running. So hopefully it'll show up here in a second. It takes a little bit for the JVMs to come to life because, okay, here's one. One just came in. So now there's 2 pods running. And what you'll see is some of these circles start to drift over to this pod. So what's happening is Akka is seeing this. Now there's the 3rd pod's in. So Akka now is seeing that, oh, I've got these other JVMs that have joined the cluster. And without too much pain and suffering on our part as developers, activity starts to move over there. So Akka is seeing that there's more capacity. You can kind of see here things are drifting over. So what are all these little circle thingies? So again, think of this as a microservice. The little blue circles out on the perimeter represent entities. So an entity could be something like a bank account. It could be a shopping cart. Something that has state. Okay. The green circles represent shards. So shards in this case, it's just for distributing entities across the cluster. And then the circles just off the center, these represent pods, and they also represent single actors running on in each JVM. So that's what's happening here. And then these little red ones that are popping out of existence, what's happening is that, let me go back to the live system, is that this is simulation, but this is a simulation of what's really used for doing like event sourcing and CQRS and a microservice. When new entities come to start up, they show up here as dark blue. When entities are no longer needed because they're not doing anything, they'll time out and they'll shut themselves down. So that's what you see when the little kind of pink pop out. Those entities are shutting themselves down. So I've kind of got this, it's a little artificial because I got this thing kind of running fast with a short timeout for demonstration purposes, but the mechanics are the same. So the idea is that this is a reactive system. And before I get into that, I want to show you the project, a little bit of the project. So let's take a look at the Java project. So this is just a standard Java Maven project. If you look at the POM, there's nothing really spectacular about it. It's a POM. It's got dependencies, blah, blah, blah. And then it's got 2 plugins that I added to make this work for Kubernetes. One is a plugin that creates a jar or a self-contained jar, right? All the dependencies go into one big fat jar. And in that, I describe what's the main class, what's the class that starts this thing up. So it's a class called runner. The second plugin creates a Docker image. So this plugin has things like what ports this plugin or this container uses. It has the command that's used when the Docker container starts up, it's basically running a jar. And those are the main things. So this runner class, let me show you that. This is just, nothing spectacular. It's just, it has a main method, it invokes a method. And one of the first things that happens in this method is we start up a actor system. And you can think of an actor system as kind of a glorified thread pool. It manages lots of multi-threaded activity, but it's more than just the thread pool. Kind of way more than just the thread pool. But it's, you can think of it as a kind of a glorified thread pool. And then, and I'll get into this later, but this thing doesn't do too much. It starts up a couple of basic actors, and then the system kicks off, and we're running. The other thing I wanted to show you was on the Kubernetes side, there's a few YAML files that are here. And I'm no Kubernetes expert. I just did enough to make this work, and then I was happy. But the main thing that's being described in this YAML file is for deployment is the Docker image, the image name and the tag. You can see that here on line 27. And there's other things like replicas. So I'm saying when this thing starts up running 3 JVMs in 3 containers and 3 pods, okay? And it also has some definition of the ports that it uses. But without too much ceremony, again, on the Java side, I just want to run my jars, right? Just make it easy for me. And this is the closest thing I've seen to really making it easy. Here's a jar, run it. Run n number of copies of it. Don't bore me with the network details. Don't bore me with anything else. Just like take away a lot of that stuff and just run it for me, which is really nice. But what we end up getting is what we've been talking about. Reactive has become very popular in the last few years, but we've been talking at Lightbend about Reactive since like 2013, not 1913. And with Reactive, it's not just reactive programming, like asynchronous programming, things like that, which we do, which is cool, which is great, and it's great that a lot of other tools are doing it as well. But it's also reactive systems. And this is the thing that caught my attention at HP, is I wanted to build a system that no matter what was happening behind the scenes, from the perspective of the users, it was always responding. And as described in this Reactive Manifesto, which you can pull up on reactivemanifesto.org, to be able to be responsive all the time, you got to be able to handle spikes in load, and you got to be able to handle when things break. So in a way, I've kind of showed you scaling up. We started with a single pod, a single JVM, and say it scaled up to 3. Now that could have happened because the load went up. Say the CPU utilization of the one pod got high, and this is what Kubernetes does. Kubernetes can be configured to see that and go, oh, and under this condition, when the memory is tight or the CPU is tight, it will auto-scale for us. Beautiful. And then on the Akka side, all Akka does is sees that more JVMs, more nodes have joined the cluster. And on the Akka side, it goes, I've got more capacity. Let me start moving actors over there. Let me start doing work on those other things. So in a way, you've got Kubernetes handling things on the outside of the JVMs, or, the coarse-grained parts of it. And it does it really well. And then Akka's handling things on the inside of the JVMs. So showed you an example of scaling up, but let me give you a quick example of failure. So one thing I did with this little UI is if I click one of these circles that represents a pod, it'll shut down the JVM. It'll do a system exit. So we lost the pod. Everything that was running on there was gone. Now, these shards are fixed. There's 15 shards configured in this system. So there's always going to be 15 green circles. So what happened was some of the shards that were on that node that just died were brought up on the remaining nodes. Now, Kubernetes freaked out. He said, wait a minute, there's supposed to be 3 pods running. I'm down to 2. So Kubernetes goes, I'm going to start up another pod. I'm going to start up another JVM. So you see it's already back. I killed one, and so Akka reacted on the inside to deal with that while that failure was happening. But a few seconds later, or maybe 15 whatever seconds, another JVM starts up and rejoins the cluster. So this is kind of that beautiful relationship, because this is the part we were missing. Without Kubernetes, we needed some other mechanism to do something like you're running in a cluster, you lose a node. How are you going to get that node back? Akka doesn't help you with that. But Kubernetes does. That's that beautiful relationship part of things. So there's those entity actors, these little blue actors on the perimeter. Again, they represent state, the state of your order, the state of your bank account. And as an example in this diagram, what I'm trying to show here is, say, you are on a client, I'm on a client, and somebody else is on a client, and we're doing something with a specific entity. So our client, say, is sending in messages or requests, HTTP to the microservice saying, hey, I want you to do something for entity 64. So we're going through a load balancer, though, so we don't know where that HTTP request is going to land in the cluster. But that's not an issue because, say, your request to do, comes in to this one node in the cluster, and what happens is that, and I'll show you the code for this in a minute, there's a quick lookup that says, oh, this is for entity 64. The thing that's looking up goes, oh, is that something that I manage in this JVM or not? And it goes, oh, no, this isn't for me. This is for this other node. So the request gets forwarded to this other node. So that's what I'm trying to show here. If you follow the blue line, it goes to this top left node. It sees that it doesn't belong to that node, and it forwards it to this other node where it does belong. So the other node gets the message. It goes, oh, this is for entity 64. Is that one of mine? He goes, yes, it is. Okay, what shard is that for? And it knows what shard is for. So it forwards the message to the shard. The shard goes, oh, this is for entity 64. Is that one of mine? Yes, it is. Is there an actor alive for entity 64? If there is, it just forwards the message. If there isn't, it creates the actor for that entity. The entity comes to life. And typically, in a real application, it recovers its state from a database, like just doing a query against a database. Or more often, the pattern is using event sourcing and CQRS. That's a whole other topic. I can't go into it here, but it fits very nicely if you're aware of event sourcing and CQRS, or you're doing it. This is a really nice pattern for doing those things. In any case, this is kind of the basic mechanics that's going on, is that in the cluster, requests can land, actors can talk to each other just as easily within the same JVM as they can across the network to multiple JVMs. The same code to do that, and I'll show you in a moment. And then the nice thing, though, is that it handles this stuff when things change, when the nodes in the cluster changes, like we went from 4 nodes to 3 nodes, the entities get redistributed in the node that went away. And the Akka part is managing that. So let me show you a little bit of how that works back in the project. So in the project, there's not too many classes here. I try to keep this as basic and simple as possible, but to show something interesting. So there's this, what I call this entity command actor. So what this actor is doing is that it's simulating traffic. So I'm not doing any kind of HTTP. I wanted to factor that out and keep this thing simple. To run this, you just run the JVM, run that main class, and everything starts up. And one of the things that starts up are these entity command actors. So periodically, this guy is generating a command to a random entity. And I'll show you how that works. So when you create an actor, this is Java. You can see it's just a regular class. Extends a basic, an abstract class. But there's this. The one thing that you do have to set up is, how do you handle messages that are sent to an actor? So I haven't really talked about actors too much, but the actors are fairly simple things to think about. Actors are, like, this is just regular Java, but nothing external invokes any of the methods on the actor directly. It's all indirect through asynchronous messages. So it's like you and I texting, right? I text you a message, you text me back a message. Those are asynchronous messages, right? That's how we communicate. That's the only way, and the messages go through Akka. Now, this is a highly optimized process. 10 years of building this thing, hardening it, optimizing it. This goes really fast. For example, we routinely run tests when we do builds, new builds, and it's something like 40 million messages per second per JVM. Internal, it's very optimized. A lot of people, when they first look at this and we start talking about messaging across the network and actors talking to each other via messaging, and it's like, oh my God, this has to be very heavyweight. But in reality, it's a highly optimized environment to do this. So in any case, what this actor has done is it set itself up to send a message on a schedule, send a message to itself. And I'm only using this so that when it gets this tick message, which is just a string, I invoke this lambda called tick sending. And this is the line of code that I use to send a message to the actor that's going to handle the routing for me. So this code I wrote, all I care about is generating, I'm simulating like getting an HTTP request, creating a message, and firing it off to an entity actor. Now I'm delegating, and this is a very common pattern when one actor delegates to another actor, I'm delegating the routing to another actor. It happens that this actor is, I'm calling a shard region actor, and that's a kind of a out-of-the-box feature with Akka. For cluster sharding, there's a simple way for you to set it up. That runner class has an example of that. But this is the code. If I'm sending a message via tell, and this command method, let me just show you real quick. It's just creating a command message, and I'm generating a random entity, and its IDs 1 through 100. So I'm just randomly generating a message for 1 through 100. That's all I'm doing here, just to simulate traffic. And then it's doing a tell. But back in here, it's like what I'm simulating is I don't have the HTTP part, but I do have the part where it's received the HTTP request for, say, entity 64, and you build a message and you send it to entity 64. And this shard region actor handles the routing. And the routing is kind of trick. But I'll show you an example where I did my own routing in a moment. So this command actor sends off these messages, and they go off to an entity actor. And an entity actor is just another class and sends the same abstract base class. And again, I have to define, what do I do? How do I handle the incoming messages to this actor? And there's two ways to do it. It's called untyped, which has been around for a long time. And then we recently announced typed. So it's a whole new pattern for handling messages in a very strongly typed way. So when I receive a command message in this actor that was routed to an actor that's created specifically for a particular entity, like entity 64, I invoke this command method. And in the command method, typically what's happening is a command comes in, say, add an item to a cart, or do a deposit, do a withdrawal, and that gets transformed into an event. And the event is stored. Or you're just doing like a CRUD-based database change. In this sample code, I'm not doing any of that. I'm just kind of keeping it. I didn't want to have you add a persistence, start up Cassandra or start up MySQL or Postgres or something like that. But you can kind of see here, fill in the blank here. This is where you do persistence. So the other thing, though, is that the beauty on the Kubernetes side is this whole load balancer feature, which is very nice to have. This whole capability of reducing the number of nodes, either because they failed or because you want to scale back. If I go to Kubernetes, we're running at 3, and I scale back to 2. It happens really fast. The node goes away. The shards are redistributed across the cluster. We still have 15 shards. They come back really quick. This time, Kubernetes isn't going to start up a third node because I told it only to run 2. And just real quick, event sourcing in CQRS, command query responsibility segregation, been around for some years now. For microservices, a lot of people are starting to adopt this. It's a very different way of doing persistence, very interesting pattern. I personally like it a lot. I've worked with customers that are getting into it, they're finding some real value in it. It is different, but basically the idea is that instead of, say, you have a shopping cart object, you get to say add item, you retrieve that shopping cart state from the database, you make a change, and then you update it back to the database. The idea here is that you're not storing the whole thing as, say, a bunch of tables in the typical way we do it in a CRUD database. What you're doing is you're storing it event by event by event. So, for example, with your item order ID 64, say we first added an item, then we added another item, we removed an item, we added the shipping address, and we added the billing address. So to get the current state of the entity, you replay the events. And including things like what would normally be lost in, say, a CRUD system would be, we have the history of all the changes that occurred, including what's sometimes called negative data, like removing stuff or changing the counts. That's really interesting, especially for like downstream data analysis. Often the negative data is more interesting to the data scientist than the other data. It's like, why did they only buy this much? Well, they can do an analysis of that with this kind of data. Really interesting stuff. If you haven't looked at it, it's a very interesting topic area. Again, Akka is handling things where when Kubernetes, for whatever reason, the number of nodes changes, the shards, in this case, are redistributed across the cluster. Now, this is the one I wanted to show you, what's called cluster-aware actors. And this is where there's an actor that's aware of the fact that it has counterparts in other nodes in the cluster. And given that knowledge, they do some interesting patterns. So what I want to show you is that, this UI here, this little UI that I'm showing you in this demo, I don't know where the client's going to land in the cluster. All this client does is it hits the load balancer. And the load balancer round robins to one of the nodes in the cluster. But I got this kind of universal tree that shows the current state of the cluster. So how do I handle a situation where an entity pops up, say what I'm showing here at the arrow, on this node in the cluster? How do the other nodes in the cluster know that? How do I have a consistent view of the tree across the cluster? Well, what happens is, and this isn't rocket science, is that when the entity starts up, I got a little bit of code in there for it to send a message to another actor and say, hey, I'm here, I've started. So let me show you that real quick. We're back in the entity actor. The entity actor received a command, and down here at the end, I've got this little method called notify start. Notify start, what it does is it builds a message, it's just a serializable object, and it does a tell to an actor called HTTP server. And when that happens, the HTTP server gets this message, and it forwards it on to its counterparts. There's an HTTP server actor, one of these actors on each node in the cluster. The server actor that first got the message from the entity actor knows that it's got counterparts on the other nodes in the cluster. So to do that, I go to the HTTP server actor, just another actor, but it has HTTP in it as well. But it receives this entity, this action message, as I called it. These are just things I created myself. Nobody told me how to do it. And when I get one of these messages, I go off to this action entity method, and this is where I get the message, and I look at it and go, if it says start, add it to this tree. So I got a little tree object in this actor, okay? If it says stop, remove it from the tree. So, and what's happening is the client is sending in a request via WebSocket every 5 seconds saying, give me the current tree. and it just sends it back as JSON. That's what this actor is doing. But it needs to keep the state of the tree up to date across the cluster. But the fun part starts where it's going to forward the message. So to forward the message, there's a way in Akka where I can ask Akka, okay, hey, give me the state of the cluster. What's the state of the cluster? And I'm asking for, give me all the members in the cluster, and I want to loop through each one. So I look, as I loop through each member, I look, is this my member, the one I'm running on? If it is, skip it. And if it's not, I check, is the member up? Because members have state. They could be up, they could be down, they could be leaving, they could be joining. There's different states, but if the member's up, then I invoke another method called forward. So forward the action. So all I do here is I'm building basically, it's called an actor reference, but it's like an actor URL. It's pretty simple. So I'm building a URL, and I'm doing a tell. So this is all it took to have kind of a cluster-aware actor that could send messages to its counterparts across the cluster. So I'm managing the tree across the cluster. I know I'm going fast and this, throwing a lot of stuff at you, but this is some of the stuff that really got me excited. It's like, wait a minute. You're telling me that I can have multiple JVMs running, with a little bit of Java code, I can do things like build this tree across the cluster. And when I first heard about it, I was like, no, you're kidding. And it's like, but the more I got into it, I was like, okay, this is cool. I can do some pretty interesting stuff with it. So there's a case of what's called a cluster singleton, which is being used in this example. I've got an example of a cluster singleton. I'm going to have enough time to show you the code for it, but it's in the project. And but it's an actor, a single instance of an actor per cluster. And what it's often used for is when you have to make a kind of a single cluster-wide decision. So it's interesting, and it does have its usage. And it handles things like if the cluster singleton, whatever nodes the cluster singleton happens to be running on, if that node goes down, the cluster singletons automatically move to another node. And what it does is it's picking the oldest node in the cluster as a strategy for where should it run. The more interesting part is this whole cluster sharding. And I showed you a little bit of that in the example code, where I've got the command actor that can send a message to a shard region actor, and the shard region actor takes over and distributes the message to the right place in the cluster. The thing I didn't mention is that the entities are, entity actors are the only place where this entity gets changed. It's an example of kind of concurrency management in actors. You know, actors are really natural. They're very natural for doing like multi-threading. And this is kind of another point that maybe takes a little bit to sink in, but the idea is that there's only going to be one actor in the cluster for entity 64 no matter what happens to the cluster. You know, maybe it's on this node, but when this node goes down, that single actor is going to come up somewhere else in the cluster, but there's always only going to be one. Which leads very nicely into building event sourcing and CQRS. So there's a part of Akka that's called Akka persistence, which is the managing of writing events to a persistence store like Cassandra or whatever your favorite database is. And there's another one called Akka persistence query, which is for handling the reads, what's called the read side. So there's an event log that you were just logging in events, and that's being handled by Akka persistence, and that's called the write side. And then there's a read side, which is the for querying. And there's an Akka persistence query has a feature for that. But again, the main thing I wanted to show you was that hopefully got a little bit of a taste for it. Akka has been waiting for a while for something like Kubernetes. And we're delighted. I know I am, because I've been, like I said, I started using Akka before something like Kubernetes was around. We had to hobble some things using Ansible and some other things for doing it the hard way. Now something like Kubernetes gives us this marvelous abstraction layer, basically, like I said earlier, for running my JVMs. The project that I ran is called, it's in my GitHub repo. It's called Akka Java Cluster OpenShift. If you're interested, all the code's there, including the UI piece. There's also some sample projects that kind of progressively build up. So there's like, I've got 6 other projects here that I've listed, and I've got other ones that you might find interesting on my repo, where it kind of progressively builds, it starts out with like a simple cluster, then it gets into cluster aware, which I talked about, cluster singleton, and so on, all the way up to a full implementation of event sourcing and CQRS. But it's project by project that are kind of standalone, that, all Java, all Maven, that I try to make it easy for somebody to kind of take it and play with it and, maybe extend it or, learn something about Akka. If you're interested in Akka, I wrote a little, there's tons of material, but I wrote this little booklet a while back that's a quick read. It's a thin little O'Reilly booklet. It's free for download. It kind of doesn't show you any code, but kind of gives you the theory about how actors talk to each other. The whole thing, like text messaging, stuff like that. It's a quick read, but the intent was to kind of give you a feel for what you can do with actors. And that's it. Thank you very much. I think we have time for a few questions.
Any question?
All right. Oh, thanks.
Thank you for the presentation. My question would be related to blocking operations within actors. As far as I remember, it's a bad practice to block your actor anytime during your application life cycle. And I assume it's especially bad when your actor must respond to the master nodes in the cluster. So while it's blocking, what happens to the, how the cluster understands that it doesn't die, or it's still available but just doing some hard work?
Yeah, that's a really good question about blocking. You're right, because actors are inherently asynchronous. So the idea is you get a message, do some work, and get done really fast, right? And they don't hold threads. It's like not a thread per request. It's asynchronous. But when the thread that's running hits something that blocks, yeah, the thread's stuck. And there's a couple things. One is there's a tool that's available. It's called the thread starvation tool that identifies if you maybe wrote some code that blocks that you didn't want it to block. That's one way. But the other one is that, for example, one project I worked on used Oracle, and it's synchronous, right? We had to block. So there's this thing called dispatchers in Akka, which are really thread pools. So you can have one dispatcher for, say, all your non-blocking actors, and another dispatcher, another thread pool for your blocking actors. So it was a way to kind of partition them from each other. So we had this other thread pool for a pool of actors that were handling database requests, performing database transactions against the blocking Oracle database. But then the challenge is, and we were able to handle that, but the challenge is that actors have what's called a mailbox. So incoming messages to an actor go into a mailbox, which is essentially a queue. And the challenge is you don't want those mailboxes to fill up, because if they start to fill up, you can run out of memory. So that is a challenge. So one of the things that was implemented that I didn't talk about was our implementation of reactive streams, which is a way to handle back pressure. So if the downstream is running slower than the upstream, then the downstream can signal to the upstream, hey, slow down. Don't overload me. So what's getting more common is that when there are situations where there's a possibility of something running slow, maybe because it's blocking on a thread, on something that's not asynchronous, that it's front-ended with a stream to handle that. But it's something you do have to be aware of, that when you start writing an actor system, you really need to be aware of blocking versus not. And if something does have to block because the external resource isn't asynchronous, then you've got to be careful how you do it. So you definitely have to think about it. So
Thank you for a nice presentation. I would just like to ask about the future of Akka. So is it with Java or is it with Scala? Is it with both?
Both.
But it's back to the contribution amount, right? Like people are contributing, maybe you have some statistic and you may give some insights about.
So Akka is written in Scala. So if you want to be a contributor, it would be Scala.
Yeah.
But it has a Java API and a Scala API.
Yes, but they are not at the same level, right? They are not in sync. Like it's more on one language and then.
I'm sorry, I can't.
I'm just about back to contribution. Like people are more contributing into Java.
No, contributing in Scala. If you want to actually contribute to the open source Akka project, it would be Scala.
Yes.
Now, if you want to contribute examples, I focus on the Java community. As a developer advocate, there's plenty of people in Lipen that love Scala and talk about Scala. But I focus on the Java community. So like my projects are all Java examples. So I'm not contributing to Akka itself, but I'm contributing example code and samples and things like that in Java. Because I want to,
yes, and just one more question about your customers. As you said, you had a lot of talks to your customers, and do they choose Java or Scala for their internal solutions?
It really depends. Like for me, I took the Scala class way back in 2013. I was a Java developer for a long time. I saw Scala, I said, oh, that looks pretty cool. I went to my manager, and the manager said, yeah, I know you could pick it up, but how am I going to get everybody else trained? This is a big company. So he said, we can't do it. So but we said, hey, but we can still use Akka in Java. So it really, our customers are, some are Scala, a lot of them are Java, especially like the big enterprise customers, which is an area that we focus on, for customers for Lipen. Big enterprise customers, it's not unusual to find there, hundreds and hundreds of Java developers. It's too expensive to retrain them to a brand new language. A lot easier to train them how to use Akka than it is to train them how to use Akka and how to program in Scala.
Thank you.
Thanks. So if I'm going to be around the rest of today, tomorrow in the speaker room, or around, if you guys have any questions, you want to see more of this, feel free. I gave you my Twitter handle. You can message me that way as well. Thank you.